Okay, very good afternoon to all the students, candidates, aspirants of robotics classes. I am Dr.Abhinav Srivastava from SKAP Robotics Center. Online classroom program is there, and I am here to present you a short or brief introduction to motor selection regarding the robotic joints. How robotic joints can perform well if a well defined and well equipped motor has been selected for the performance of joints of a robot. The thing is here is that the why I am taking this part in consideration. Actually, I have got certain mails regarding the functioning of a robot. And while discussing the functioning of a robot, I have gone through miscellaneous disinterruptions or miscellaneous misconceptions prevailing in the minds of a robotic educational aspirant regarding is servo motors are highly efficient, only servo motors can be used, or any other motor can be used for deriving the forces or torque that are used for the motor selection. The basic thing here is that why motor selection is so much of gain importance in describing the behavior of a robot. Actually, I have just made a robot. For example, a robot has been made, and it should be very much easier to see that this is the base of a robot. These are A1, A2, A3 are the joints, where these are the rods connecting the A1, A2 form the links. These are called the links. Before going into the deep equations of motion of a robot with respect to its joints, it is very essential to discuss what is a joint, what is a link with respect to a simple industrial robot. And the thing is that you have to keep in mind that all the aspects, many of the aspects that encountered in the selection of parameters for an industrial robot will be same as the selection parameters regarding the humanoid robots. Some kind of torque and inertia calculations might be different, but I am very much peculiar about the fact that some of the inertia parameters and load parameters might be different, might be evolutionary more complex, but the base of parametric selection regarding a robot can be studied with the help of industrial robotics. Industrial robot forms the base of the education regarding robotics engineering. Without reading, without studying about the industrial robots, you can't switch to humanoid robots directly, and we can't say that the equations of motions governing the humanoid robots are totally different from that of industrial robots. The base frame will always be with respect to industrial robots, and that then some certain parameters like remote center compliance, RCCs, and these kind of things adds up in the more structured manner in case of humanoid robots. That's why we are discussing everything with respect to the industrial robots. That's why I have made just a single and simple diagram of an industrial robot, and that is the end effector of the robot. That is the rod connecting A1, A1, A2, A2, A3. These rods forms the links, and A1, A2 points are called the joints. If we sum up for a very basic definition, then we can say that number of degrees of freedom will be the number of joints of an industrial robot manipulator. That might be the thing. The number I am repeating it. The number of joints of a robotic manipulator can be thought of as equals to the number of degrees of freedom of that industrial robot. But this is a very preliminary and the beginner's thing. This is not, we can say, this sum up of all this kind of things pertains for all logic instincts of a robot. That is not the possible way. I am just saying it for a preliminary basis And with the complexity of robots like SCARA configurations, selective compliance, assembly robotic arm configurations, Puma configurations, articulated arm configurations, the things might add up, and number of degrees of freedom definition might change or might adds up. For a general basic 6 DOF system, we have can be say that it can be 6. It can have 6 joints. The number of joints will be equal to the number of degrees of freedom of an industrial robot in a preliminary sense. Okay. Then now coming to topic for today's topic. The topic I have written that the motor selection principles. This I'm just reviving the camera. Okay. The thing is, the topic is motor selection principles for robotic joints. The robotic joints move on the behalf how well we select a motor. If we talk about the motor selection principle, then it is important because of the fact that if the motor selection principle that generates that is basically the calculation of torque parameters. The motor selection principle basically defines the torque parameters on the basis of which we select the proper motor that can be applied to robotic joints, so that the robot can perform absolutely in excellent mode with respect to the observers, or with respect to the purchasers, or with respect to the client expectations. That's why we have taken the topic motor selection. This is a kind of we can say the drive mechanism with regarding the robotic joints. So that's why we have taken this topic. Very important topic is there. So then first we have to formulate. Here I have not formulated this equation. I have just discussing this equation. The formulation of this equation contains a larger task. There is a complex task. Various differential motion constraints should be there to derive this equation. That can be discussed if we talk about in the later by detailed lectures. If we consider the detailed lectures, then the derivation of this equation can be prescribed, can be evolved. If we take a very long lecture to derive these equations, but I am just briefing it that for the motor selection, what we are in the phase, what we have in our mind, so that in what way we proceed to generate the basic equations for the formulation of motor and calculation of the torque characteristics. Why the torque is important? Actually, torque, we can say, if we have gone through our basic physics, we have already discussed that torque is equal to force into displacement. Torque is equal to force into displacement. Actually, in the robotics engineering, the torque has a very special significance, because all kind of characteristics regarding the performance of the end effector depends upon this torque parameter. And this, by the definition of the torque, we have torque is equal to force into displacement. That is, torque carries all this much of things that are required for effective working of the robot. That is force, that is very much requirement for the very well performed requirement for the basic functioning of a robot, so that it can handle the load. We can say that payload. So what is the basic function of a robot? To handle the payload. And how payload can be handled without force, it is not possible. That's why torque has come into existence. Without force, it is not possible to handle the load or payload, we can say. That's why the first thing that contains under the torque is the force, very much important thing for the working of a robot. Then displacement, how much the displacement should be regarding the end effector, regarding the joints, how the joints should be displaced so that the end effector can reach the payload very effectively, can grasp the objects, and basis on these kind of things, trajectory planning has been done, which we discussed in any lecture else, whenever the time allows us. This is the thing. So that's why torque calculation is the basic funda for calculation of the motor characteristic regarding a robotic joint. So we will these equations are formulated for the calculation of torque, and I have discussed just that why torque is so much of importance, because torque contains all that things that is effectively constitute the working of the robot, both force and displacement. Now we begin with the help of a dynamic equation of a robot. What is the dynamic equation of a rigid link robot? Rigid link robot means the links are not fluctuating. Links are at certain instance of time, the links are very much at their position in certain stable for a certain instant of time to achieve a payload, to work on a payload. After discussing these equations, we also incorporate certain things like dwell time. Dwell time is very much important in case of robotics engineering. The dwell time signifies the time during which the robot arm remain at the fixed position while its end effector is working. Robot arm is fixed to a certain time instant, and at that time instant the robot end effector is working, because if the end effector is working as well as the link and joints are also unstable position, then how the end effector will generate a proper force to grasp an object. That's why dwell time calculations are also there. I have not write it down here because of some space complexity there on the board. We have certain very much important things to discuss rather than that of these subsidiary issues. Discussing the dynamic equation of general rigid link manipulator is the MQ for n degrees of freedom. This is very important thing I have written is that this equation is for n degrees of freedom. The degrees of freedom has very important consideration in the manufacturing of the equations of a robot. Number of independent motions considered by a robot in a workspace constitutes its degrees of freedom. If the number of degrees of freedom of a robot increases, obviously the thing is robot is more precise in their calculations. The general observation is that. So for n degrees of freedom, we have this equation where m signifies the inertia matrix. The thing is obvious. When we grasp an object, when the proper linkage mechanism is in motion, the inertia factors generate, and we will consider here in the form of m. M is the inertia matrix. The important thing here is that all the operations has been done on the arguments taking q and q dash and q double dot. Q dot and q double dot. Where q I have mentioned in the above screen, you can see that q is the joint position of the joint. Obviously, if the q is the position of the joint, then q dash, that is q dot means dq by dt with respect to q dot is equals to dq by dt. Q double dot is equals to d square q by dt square with double differentiation acceleration. If q signifies the joint position, obvious the thing is that the q dot signifies the joint velocity and q double dot defines the joint acceleration. If we take these as an arguments, then the equation of rigid link robot will be dynamic. The dynamic equation of a general rigid link robot will be mq q double dot. That is, m is the definite positive symmetric matrix, positive and definite matrix. What kind of matrix? That the inertia matrix. We will discuss in the elaborate lecture what is inertia matrix. I am just discussing the equation here also. What are the constituent of a dynamic equation regarding a rigid joint robot? MQ q double dot, where q double dot which signifies the joint acceleration, plus C. What is C? C is the Coriolis and centripetal matrix. What is Coriolis and centripetal? You have to study, and you were in the position in your previous semesters. Then what is Coriolis matrix? Coriolis, you have studied that in the form of Coriolis acceleration as well as centripetal acceleration. If I talk here, then I can give us a very slight introduction to that. Coriolis signifies anything that is Coriolis, either acceleration. Coriolis signifies these the kind of acceleration, kind of a thing, kind of a parameter that is generated on the basis of the rotating frame of reference, while centripetal arises on the basis of what external push, what external thing, external either force that tends that machine in a rotatory motion. That is the difference. Coriolis signifies the quantity with respect to rotating frame of reference, while this signifies when the external factor has been given or push has been given to make the thing to revolve around a circular path. That is mentioned in the C. The C parameter signifies the Coriolis or centripetal matrix. The other thing important here is to be considered is that M and C are matrix. That's why we have taken R to the power n cross n, where n is the number of degrees of freedom. Here both C and R, since these are the matrix, hence M and C both are considered as inertia and centripetal or Coriolis matrix defined in terms of R की power n cross n. That means n is single, n is a number of degrees of freedom. Then comes to the next part, that is G. G is not a gravitational acceleration, not anymore here. G signifies the gravitational torque. I have written the gravitational torque generated by the gravitation. We have also encountered it. If we formulate the position matrix regarding the robots, we have encountered a certain equation called Denvit-Hurtenberg equation. This equation gives the precise position analysis as well as velocity analysis with respect to base frame and end effectors frame. That we will discuss later. Okay, that's the gravitational torque. Next, the important thing is these argument of gravitational torque will be joint position. Argument of the Coriolis and centripetal acceleration will be the joint position as well as joint velocity. This is a very important thing. Then on the right hand side of the equation will be the tau f plus and tau j. Tau is the joint torque, that is belongs to R. R signifies for real numbers. R की power n, that is the joint torque, and tau f is the interaction torque with the environment. One torque is of joint, that is the joint, and work torque is of end effector. And these torques should match to generate the total dynamic equation. So you can see very easily that these equation, each and every member of this equation is a torque, generates torque. This is also a torque. This is also a torque, and this is also a torque. That's why how we can match the dimension analysis, because all these equate to torque parameters. So this is very important to see here that all these individual entities generate a torque. This is the very important thing. And next important thing is that I have summarized these equations in the form. Then what kind of individual torques and how can we calculate these torques? We can calculate the torques in the form of two things. First is the accelerating torque and second the decelerating torque. The thing is that when we grasp an object from the base, from a certain sleeping position to an active state to grasp an object, some accelerating torque should be there. And when we release an object or we have to backlash, then we have a decelerating torque should be there. So both of these torques should be considered here, so that the both grasping of the object as well as reversal or retrieving of something should be easily monitored and mounted. That's why we have calculated two torque parameters apart from this equation. The first parameter is the accelerating torque and second is the decelerating torque. That's why I have discussed here. The accelerating torque, always by the name, as the name suggests, accelerating, we have accelerated, and decelerating when we have reverted or decelerate. In the acceleration, the final velocity is more than the initial velocity. In the deceleration, the final velocity is always, in the acceleration, the final velocity is more and initial velocity is less. In the deceleration, final velocity is less and the initial velocity is more. That's why both torque calculations have been done for the acceleration as well as deceleration. Now the other important thing here to consider is that I have written the accelerating torque. The formula for the robotic joint for accelerating torque to generate accelerating torque to the end effector T accelerator is called JL alpha acceleration plus TL plus BL omega pk. Some important terminologies to discuss here is very much of concern and should be very much noted down. JL is the load moment of inertia. What is the load moment of inertia? That in the very short term, when we grasp a load, either the load is in revolving position or the load is at different position from its center of mass. That is the load moment of inertia. That's why we encountered here. Then alpha acceleration. Alpha acceleration is the angular acceleration. Angular acceleration of what? Angular acceleration of the wrist. Is the angular acceleration of the wrist to grasp an object. Then TL is the applied load torque. Then BL omega pk. BL is the load viscous damping. We are very much sure that these kind of viscous damping things are previously discussed in the previous lectures. Then omega pk is the peak angular velocity of the motor shaft. BL is the load viscous damping, that is the opposing torque that is proportional to the velocity. The main thing, I'm just summarizing it too early, that if we compare acceleration, deceleration, torque, all things are the same except the BL omega pk has not been taken there. Why that has not been taken there? Because viscous damping also already supported deceleration torque, because these forces are negation forces. When we decelerate with certain torque parameters, then viscous damping is already there, it supports in that. That's why we have not encountered here. And in the second term we are here grasping that TL applied load torque is a negation side there, because in the deceleration the load torque will get reduced, will have to got distracted from the original equation, from the original parameter, that is this angular we have to subtract the load torque from the angular deceleration parameter, so that our final velocity will be more than the initial velocity. Because in the acceleration we are discussing that in acceleration the particle is accelerated, the final velocity is more than the initial velocity, while in the deceleration the final velocity is less than the initial. Then how can we achieve is that? We can achieve by when we subtract the applied load torque from this factor, that is load moment of inertia into angular acceleration. So many of the students might not be very much aware of certain things. Actually this thing is of very much importance if we have a prior some knowledge of basic like viscous damping and these kind of things. Another thing important here is that we have a certain equation for calculating the angular acceleration, that is alpha acceleration is equals to omega pk by ta acceleration time. This is also a very important thing. Omega pk, that is the peak angular velocity of motor shaft. Peak angular velocity can also be calculated in the form of this can be used for the calculation of angular acceleration. Omega pa by t acceleration time. If you have known the acceleration time to accelerate the joint to a certain payload, then by dividing the angular velocity with the help by acceleration time, we can calculate the angular acceleration. This should be in concern. That's why I have just specifically mentioned it that here. One thing important, last thing is there. The RMS value, in spite we have calculated acceleration, deceleration, and RMS value of torque has been taken in the selection of the motor because of the fact that the RMS value contains the energy content for a signal. Main energy content has been generated from the RMS value. That's why, and this RMS value is contained in this acceleration, deceleration. A formula is there that collect the RMS value by some mathematical operations on T acceleration and T deceleration, and finally we compute the T RMS that contains the original energy content that has to be sorted for the selection of the robotic motor for the selection of robotic joints. That's why I have just written some equations. You have to be very careful in defining these kind of things. Some prior study is needed. Without this can be of much difficult or complex in perception. But actually, if you have certain basic knowledge, then these kind of things are not very much complex. But you need some prior knowledge, some prior reading. Then after this, you can see this video, that you can understand. Okay, I'm just discussing a brief aspect, not a full and final aspect.